Swayam Prabha. Digital India. Educated India.
Okay. So far we have seen attacks at the link layer and the network layer. We will continue with the attacks at the transport and application layer. So at the transport layer, before we begin, let's understand TCP a little bit, because we are going to look at attacks against TCP. So a lot of you are aware that TCP, there is a handshake before you can start sending the data. How many messages are sent as part of this handshake? 3 messages, which is basically there is a SYN. So basically this is the client is the one that is establishing the TCP connection, and server is the one that is responding to the connection. So you send a SYN, then you will have a SYN ACK, and then you have an acknowledgement again. So this is the famous 3-way handshake of TCP. Okay. Apart from this, another thing which you should also be aware of is that, okay, this is the establishment of the connection. You can also close a connection through this FIN. So again, if this guy wants to close a connection, it will do a FIN, and then there is an acknowledgement for that particular FIN. Okay. This will close only one side of the connection. If you want to close the other side of the connection, this guy also has to send a FIN, and in response to that, this guy will send an ACK. Then both sides of the connection are closed. Okay, so this is some background. Apart from this, you should also be aware that there is something called a reset option in TCP, where whenever you send a reset, the other guy will not care what is happening, it will just close the connection. Okay, so this is the purpose of reset whenever you want to close the connection. Now, in the attacks that we are going to cover, few things you should be aware of is that there is a sequence number that is used in the TCP packets. Okay. This sequence number is there as part of SYN, SYNAC, ACK, and afterwards whatever data you are exchanging, this sequence number will be there as part of those data packets as well. So one of the things you may have heard of is that this sequence number is randomly chosen whenever you start a connection. Both sides choose a different sequence number. So this will choose some sequence number X, this guy will choose some sequence number Y, and acknowledgements are acknowledging that particular sequence number. The question to you is, why is this sequence number random? If you have covered networks, can you tell me why is the sequence number random? So just again, this ACK is acknowledging X plus 1, this will send sequence number Y, this will acknowledge Y plus 1. Why is the sequence number chosen to be random? Why not just start with 0? It's just much more convenient in understanding the sequence number space. So when TCP was designed, there was no security in mind. So later, of course, we will cover security, but TCP was designed in 1980s something. At that time, they didn't bother much with security. So it is a different reason from security. People know what it is.
Both should be random so that they don't overlap on each other.
Which? Sequence. So the answer is that you want it to be random so that 2 connection packets don't get merged with each other. So oftentimes what happens is there is a client A that establishes a connection, let us say this is A, this is B, and it chose, let us say, starting from sequence number 0. Okay. And something has happened and you have maybe gone until sequence number, let us say 15,000 something. Okay. And then somehow you close this connection, and A again established another connection with B right immediately after, and again it started with 0 and let us say quickly ramped up and it went all the way till 15,000 again. Okay. If it happened that some packet that it has sent here got delayed in the internet and then got re-injected here, as in got delivered to B after a lot of delay, the receiver, because this packet falls in the same space as it is expecting, it will accept that packet, which is not valid for TCP. TCP, you want other packet connection should not overlap with your thing. So, if you were to choose randomly, the sequence space will be different, where that guy's packets cannot be interjected into the next connection. You will drop it because it does not fall. Remember, TCP is also a window based protocol. You are probably aware of the sliding window. So, what the receiver does is it expects at any given time packets only in a given window, and this window it has a sequence number range from here to here. So, x to y, only within this window it will accept. Anything that does not fall in this window, it will drop those packets, because it is a sliding window protocol. Now, when you choose random, the probability, again this is a probability thing, you cannot say with 100% guarantee it will not. Probabilistically, because the sequence number space is very large, if you chose random, you will not end up accepting the previous connection packets in the current window size. Okay, so, that is one of the reasons why people chose a random sequence number, but this turns out that it helps in security as well, as we are going to cover next. So, here before that also let me talk about this reset business, which is again a very useful feature in security. Suppose Mallory here is, so there is A, there is B, Mallory is pretending to be A. So, in the IP address it put A as the source and destination as B. This is the network layer header. Okay. And it sent some SYN packet at the TCP layer and contacted B, choosing some random sequence number X. Okay. Now, B in response to this will assemble a packet with the source as B and destination will he put M? Because it does not know that Mallory is sending this. As far as the packet is got, it got from source as A, so it will put the destination, and within that it will again choose a new SYN Y and acknowledge the earlier X plus whatever X it will acknowledge, the sequence number X. So, this packet B is going to send. Now, lot of times people assume incorrectly that if Mallory took on A's IP address, where it is sending this by taking on A's IP address, when B sends a packet with destination as A, who does this packet go to? People assume it will go to Mallory. It does not go to Mallory. Mallory just took on A's IP address and put it as part of the packet. Routers will forward the packet to whoever A is. They are not going to send it to Mallory, because routers will do their own routing. So, this packet actually will reach A, because the destination is A. Mallory just assumed that identity, but the routing framework will send it to the right destination. Now, A will see this packet, it will be listening on some port corresponding to whatever this destination port is, and it will say that what is this, I have not even started this connection and now I am receiving a packet with certain parameters. So, immediately the default behavior for this is reset. Whenever A receives a packet for which it has no idea that there is a connection or whatever, it is going to set this reset bit in the TCP, because it can't even figure out what this X business is or this Y business. It will just do reset with acknowledging maybe Y plus 1, because this has a Y, and this guy will close the connection. Okay, so, if Mallory is trying to do something as part of this, if the packet went to the other guy who it is spoofing, that other guy will close the connection through reset. This is something to keep in mind. Okay. So, with this background, let's again now look at a few attacks. This attack, it is called TCP SYN flood attack. It's a type of a DOS attack where the idea is that you are overwhelming the server who is using TCP by sending. So, this is the server and you are bombarding it with lot of SYNs. So, why does this attack work? Again, let us get into a little bit of a detail. In fact, attack there are a lot of details, I will get to that, but first is whenever you are receiving a connection which is the SYN, what the server does is it will allocate some memory to save some information about this connection. Okay, what does it save in this? It typically saves, okay, it has used this sequence number, this is coming from some host A, and maybe some advertised window or maximum segment size is this much. Some information about that connection it will save, because it needs to keep track of what this connection is. And each time it gets a SYN, it is going to allocate some memory to keep track of that particular connection. Now, when you do the SYN, all you are doing is you are exhausting that memory. That is why it is a denial of service attack. Now, if you, for example, if you have assigned, let us say 2 GB for this, and each of this, let us say, is taking some, let us say 10 KB, whatever it is, those many connections you can accept. After that, there is no more memory, and thereby you are going to have to drop connections. So, that is the basic idea of SYN flood, where you are exhausting the memory that the other endpoint is. But of course, if the reset comes, you will clear up this memory, okay? Or even if the connection is established, you move on to some other memory. Not this is this memory is basically for before connection gets established. That is, the 3-way handshake has not completed yet. For that you allocate some memory, and that is a fixed amount of memory. Okay? So, that is the basic idea of SYN flood, where for this attack to succeed, memory, when it is sending the SYNs, can it use a same IP address all the time? So, in other words, this SYN packet it use memory or whatever IP memory, and so on. Can you launch this attack? Why is this? Why won't it work? Huh? These are different connections. You could, for example, use different port numbers for each. Then it will be a separate. TCP, remember, also is a connection is identified by a 4 tuple, which is source, destination IP, and also source destination port. If you vary one of these parameters, it is a separate connection. So, it could use different port numbers to do it. Source port, if it will vary, it will be different connections. So, why is this not often used? Server can do something to block this very easily. If memory is using the same IP again and again. Yeah, so you could do filtering based on IP. Lot of times these servers, if they are seeing lot of SYN packets that are coming from a specific IP address, they are just going to drop those particular packets. So, this attack is harder to succeed because you can use IP filtering. Okay, so, that is one aspect. What if I did this, where Mallory is spoofing Alice's IP address and sending? Will this attack succeed? Yeah. So, in this particular case, while Mallory is sending this, the axe for this will go to A will reset immediately, and once it resets, all this memory will get cleared up again. So, this attack will also not succeed if A is up. So, whenever you want to launch the SYN flood attack, either one option is you employ a botnet. Okay, botnet is all compromised machines, where if you get hold of 10,000 compromised machines, you use their IP addresses. That way you do not have to stick with one IP address, because one sticking with one IP address means it will filter it out. Second is that because this botnet is under your control, when you get the SYNAC in response to this, you just ignore, do not respond to it, just drop that particular packet. That way this memory will stay alive until you get this ACK, the third ACK. So, as you can see, there is SYN, there is SYNAC, and then there is an ACK. Okay, until this ACK comes, this memory keeps getting allocated, as in it stays there. Once ACK comes, then you move on to some established phase and there is some other memory you handle there. So, this TCP SYN flood attack is handling this memory. So, you will not send this ACK with a botnet. Okay, so, this is one easy way to launch TCP SYN flood attack. Okay. Now, what is the solution to this? How do you defend against a TCP SYN flood attack? So, one, as I said, is filtering, but this will only work if you are launching the attack from one single IP address. Okay. The other is, so one is saying will increase the amount of memory. Will that help? If you increase the memory, that guy will increase the connections also. There is, it's a, what is it called? How much can you? It's a who has more resources is the question. And generating SYNs is an extremely easy task. You can easily overwhelm. SYN hardly is like some, how many bytes is it? Few bytes. Very easy to generate FINs at a very large scale. So, if that guy increases memory, you will increase the number of SYNs. So, that is not going to help.
By limiting the IP addresses?
That is what I am saying is that IP addresses, if you are taking a single IP address through filtering, you can drop those. So, that is one mechanism, but oftentimes you won't use a single IP address because you know that that guy will put a filter. You will want to use multiple IP addresses. Okay. Oftentimes in these attacks also, as I mentioned, you also like to spoof someone else's IP address because you do not want to be caught. Yeah, you had a question. We will get to that shortly. There is something called SYN cookies, I will explain that shortly. The other mechanism often in these type of things when you are trying to spoof someone else's IP address. So, basically Mallory is trying to take on A's IP address. Okay, because fine, it may filter, but filtering means they know that someone is bombarding from this, they will invoke the law agency, the police, and they will try to catch this Mallory. So, Mallory will not give her IP, she will take A's IP address and tries to launch. Okay, so oftentimes the solution against this type of spoofing is called ingress filtering. This is employed by routers. So, let me tell a little bit about that. So, for example, this is an organization, let us say IIT Bombay. Now, this IIT Bombay organization has been assigned certain IP address block. So, I am just making up some number. Let us say it has been assigned this block 13.12.***. That means all the machines that are part of this particular organization will have some addresses like this, okay, where 13.12 will be fixed, whereas others can change. Okay. Now, there is a router that is going to serve this organization, and this router knows that all IP addresses within this belong to this block. Now, if Mallory is sitting somewhere here and now it is trying to spoof someone's IP address, which is let us say 205.16.5.7, this router knows that this IP address does not belong to my organization, and routers are configured to drop such packets. They will not send out packets where the source IP does not belong to that particular organization. That is called ingress filtering. So, spoofing is much harder. So, if you generally want to take on some IP address and send a packet, the router that is sitting will drop it. But of course, this again there is a black market for these organizations which will say we will not do such things. So, you take IP address from such service providers who do not employ ingress filtering. So, that is also possible. So, this is another kind of solution where with this you can mitigate to some extent, but as I said, if you bring in botnets, then there is nothing you can do. I mean, these are valid machines with valid IP addresses belonging to that particular organization itself, but you have complete control over it. So, if you use a botnet and try to launch SynFlood, it is very, very hard to prevent those type of attacks. So, that brings to the third option, which is what is called a SYN cookie or a TCP cookie. So, this is a clever idea where the idea is that, see, this memory that you are putting here, you are saving certain information about the connection, and because of that you are having to allocate this memory. The idea here is that I do not want to allocate any memory, but somehow I need to still have that state. Now, where do I keep that state? So, this is similar to web cookies. If you are aware of web cookies basically put all the state you need into a cookie and then send it to the client and ask the client to give back the state whenever they want to contact you. So, the same idea is here. So, what is happening here is, so this is A, this is some B, and it chose some sequence number. Okay. Now, what B is going to do is it is going to, so this shows some sequence number X. As I said, there is port information, IP information, maximum segment size, whatever you need to keep track of, you have this information. So, what this will do is B, when it is generating the sequence number Y, which it has to send, this Y will encode the state. Okay, by encoding the status, it will take some of these parameters and assemble the sequence number, where once it gets back, for example, this guy will acknowledge Y plus 1. From this Y plus 1, it will find out what Y is, and from that Y, it will reconstruct the state that is needed. That way, you do not have to maintain the state anymore. How exactly it is done, I will not cover the details now, but you got the gist. The gist is that whatever state you need to maintain for this particular connection, you will encode it into the sequence number, and the other guy, when it is replying, it will anyway have to tell ACK that sequence number. So, once you get the ACK, from that it will reconstruct the state again, and of course, you will verify that the state matches the IP address port information that is there in this packet. If it matches, it will assume that this is a correct thing and go ahead. Okay? So, this is the basic idea of cookies, TCP SYN cookies. There is more detail there, I do not want to get into too much detail. So, I think this is enough to understand the TCP SynFlood attack. So, next we will see TCP spoofing attack. So, here, okay, actually before spoofing, maybe let me cover TCP session hijacking, then I will cover spoofing. Okay, in TCP session hijacking, basically there is a SYN ACK X, this is Y, this is X plus 1, and then there is an ACK which is Y plus 1. Okay, this is the TCP handshake. the idea is that Mallory, there is a session going on between A and B, and Mallory is trying to hijack that session. Basically, Mallory wants to inject some data as part of this connection and get A or B to accept the data. Okay. For this to be successful, for Mallory to inject the right data, what all information does Mallory need? SYN and X. So, first let us to construct this data packet, what does Mallory at the network layer, what does it need to do? It needs to create the IP addresses, for which anyway, since it is spoofing B as the source, in this case it will put B, destination as A. Okay. And it also needs at the transport layer to construct the port information also. This is probably between some source port and destination port. Okay. It needs to get that port information also correct. Only then the other guy will accept this particular packet. You need to get both IP addresses correct and the source and destination port also correct. These things often are very easy to guess. It is not that hard. For example, if you know A is some neighbor and contacting Google, whatever it is, you know Google's IP address. If it is a web server, you know it will be port 80. This guy's whatever source you can maybe guess somehow. If you are on path means you are able to see these packets. Things are very straightforward. You can immediately figure out what the source, IP, destination, everything is. Okay. But in general, this information is lot easier to guess, but the difficult part is guessing the sequence number if you are not on path, because that guy will choose some random number and it is over a very large space, 32 bits. So, for you to guess the correct sequence number is not going to be easy. But for this attack to succeed, in this packet you have to put the right sequence number, because as I mentioned, TCP is a Windows based protocol. It will only accept packets in the window that it is expecting, and the sequence number has to be in that window, only then it will work. So, this is the particular idea, and in this hijacking, of course, when you put some data, this A may act on the data, and also this can also be a reset packet, in which case it will close the connection also. So, for example, if two are talking, you do not like them talking, you send a reset packet, you will close off the connection. So, that is what Mallory is doing here. Okay. So, the basic idea again here is to construct the right packet, you need the right amount of data. If you are on the path, things are very straightforward. If you are off path, you have to guess these values, and how well you can guess is a function of how well the sequence numbers are generated. If the sequence number generation is predictable, which in fact earlier versions of TCP used to do that, they were random in the sense that they were not starting at 0, they were starting at some other number, but it was a predictable start. You always can predict that this guy will now start at this level, in which case you can easily inject this data with the right, because you can now predict what the sequence number is. Okay. So, that is the challenge of, so basically whatever is protecting is being protected by your sequence numbers correctly, because you cannot guess the sequence numbers easily. So, that is the protection TCP offers. This is the TCP session hijacking, and now going to TCP session spoofing. So, here the idea is there is Mallory. Mallory is acting as A and sending a packet to B using its own sequence number. Okay, sequence number X it has used. Now, for this attack to be successful, now B will generate some packet which is going to go to A now, and if A saw that packet, it will reset. So, if you want to succeed in TCP session spoofing, you have to bring down A, because if A is in the picture, it will reset the connection. Okay. So, here multiple things M has to achieve, basically it has to bring down A. Not just that, it also has to guess the sequence number Y B is going to use. If you are able to do that, then this session spoofing will succeed. So, bringing down A, oftentimes you will use SYN flood to bring it down so that it cannot respond. That is a DOS attack you launch on it. And guessing Y, as I said, if it is on path you can easily guess it. If it is on off path, it is much harder these days to do it. So, that is what protects TCP to some extent. Okay, so, this is the TCP session spoofing. Yeah.
I mean, if A is down, so where B will send?
B will send a packet, that does not matter, since A is down, this guy will now act saying Y plus 1. That is what session, A has to be down, M will take on the role of A and start replying to B. You want A down to
Source IP means MS A's IP.
Yeah, it is spoofing, that is it has as in it is constructing packets with A's IP address as part of the packet and sending. Okay, so this is with respect to the current TCP attacks are basically this TCP SYN flood, TCP session hijacking and TCP session spoofing. For all this to be successful, as I mentioned, you need to be able to predict the sequence number. That is more or less what protects the TCP currently, because it is hard to predict those numbers. In addition to that, if you of course use TLS SSL, they also provide protection against these. We are not getting into the details of how TLS SSL will provide it, but those have mechanisms in place. Okay, so that is with respect to the TCP attacks. Okay. Now we are going to look at application layer attacks, where we will start with DNS, and I will also cover amplification attacks, which is a form of DOS. Okay. Any questions before we proceed?
How did we solve session?
Session, all as I said, session spoofing or even session hijacking, the only difference is random sequence number currently, or you go for TLS SSL. That is the only difference now. Okay. So, now let us look at application layer attacks. DNS is a core service, but it is implemented as a application layer protocol, and we already covered. So, often again let us cover a little bit of what DNS is. So, this is your machine, which is, let me call it A, and this is your network, which is part of, let us say, some organization, IIT Bombay, and within this there will be something called a local DNS server. So, what happens here is A, for example, in the browser, let us say you typed amazon.com, it needs to get its IP address. So, A will contact the local DNS server. How did you get this local DNS server's IP address? The DHCP server will tell you. Okay, when you are getting, it will tell you who your local DNS server is. So, you are going to contact that local DNS server, and this local DNS server will do some magic and finally tell you what the IP address for this is. Then you will assemble that packet and send it out. Now, how does this local DNS server determine this particular IP address? This you may have read about, is that there is in DNS, there is a, for example, if you look at amazon.com, it is a tier system. So, at the highest level are what are called root servers. Under these root servers, we have .com, .edu, .org, all these are there. Okay? And within .com, there are many companies, of which there is Amazon, maybe Facebook, and so on. Okay. So, this local DNS server maintains a cache. Within the cache it can have certain information, but let us assume right now that there is no cache. Now, what it will do is it will first go ahead contact the root server and tell, do you know what the IP address of amazon.com is? The root server will say, I do not know what the IP address of amazon.com is, why do not you contact the .com server, and it will tell you what the IP address of the .com server is. Now, this local DNS server will now contact the .com server. That guy will say, I also do not know, why do not you contact Amazon's DNS server, those are called TLS servers, not TLS, these are called authoritative name servers. Okay. Amazon as an organization will have a DNS server it will set up, which will know all Amazon machines host names to IP address mapping, because that is the best, I mean it is serving that organization, so it better know. So, that is, this is called the authoritative name server of Amazon. So, .com will say, I do not know, you go contact the Amazon's authoritative name server, and here is its IP address. Now, this local guy will now contact the Amazon's authoritative name server, who should be able to give answer that amazon.com IP address is this. Okay. So, that is how DNS resolutions happen without caching. Oftentimes this guy will cache lot of information. He will cache this root to IP address, com to IP address, Amazon's authoritative name server to IP address, including the specific machine of Amazon to its corresponding IP address, all that is cached. In which case you do not, but if you do not have that information at that relevant, you will again contact and get that information. So, that is what is happening with respect to the DNS. Okay. So, let me also mention here, so DNS essentially has a request and there is a reply that will come in response to that request. And as part of the request, there is a field called ID, which it will fill, it will give some number to it, let us say ID is 23. Now, typically the reply will reproduce this ID. That way the local DNS server knows to match this reply to this request. It is just an implementation ease that you send an ID, once you get the same ID you will map the reply to that particular request. Okay. So, that is one aspect, and again as I said, DNS is an application level protocol, there are port numbers involved as part of this, and of course there are IP addresses also involved. You have to construct the right packet with respect to this. Okay. So, one other thing before we cover DNS attacks you should be aware of is something called, let me write here itself, glue records. So, what these glue records basically tell is, if you see, let us take one example here where you have contacted the .com server, okay, and as part of this your query was what is the IP address of amazon.com. Okay, that was your query. Now, this .com server, as I mentioned, will say, why do not you contact maybe dns.amazon.com, which is the authoritative name server, why do not you contact this guy? He will tell, and it could stop there because that is a valid reply. Okay. Then of course, in order for you to contact dns.amazon.com, you again need its IP address. So, then the local would have to start a new DNS request, which will say, tell me the IP address of dns.amazon.com. and this again can go all the way to the root and come, okay, which is going to add extra delay in resolving this. So, the basic idea is that instead of resolving this again, whenever this, I think it's okay, let me write in a, so let me write again about glue records because it's getting a little bit. So, this is our local DNS server, okay, which contacted this .com server, okay, and what did it contact? It said I want to know IP address of Amazon.com, and this .com server could have replied saying I do not know, contact dns.amazon.com and stopped there, okay, that is the reply. Now, what the local DNS server needs to do is, again it got a host name, it has to resolve this IP address again. So, then it would have again contacted this guy saying, okay, now tell me what is the IP address of dns.amazon.com. Now, this guy then will tell what the IP address is, because .com is supposed to know the authoritative name servers of all the companies. So, instead of doing this again, what it will do is in this request itself, when it is replying, as part of this reply, it will all tell that the authoritative name server is dns.amazon.com, and in the glue record, which is extra information, it will also tell dns.amazon.com IP address is maybe 17.5.6.9. So, it is sending extra information even though that guy did not ask for it explicitly. Okay, so, this is what is called glue information, it is called a glue record. So, when we go forward, the things you should keep in mind are that there is a ID field in each of the requests, and the replies can have this glue information. Okay, these are two things for you to keep in mind. These are clear? ID field is there in the request, and replies can have glue records, which are records you did not explicitly ask for, but the other guy will send to make life easy for you. Okay, so this is the thing to keep in mind. Now, with this as a background, let us see DNS attacks.